Hey everyone, I just wanted to finish up and do a few more questions from this PowerPoint. So I just want to make sure that you guys see a lot of different ways that we could use the conservation of energy equations. So this video is it's going to be a short video, but it's going to be all about doing the practice questions. Here's the next question. Pause the video, work on itself. We'll go over in a second. All right, so we have a person throwing the ball up in the air with the initial speed. Is there a height change? Yes. It's going to end up at some height, so it's going to end with potential. Is there a speed change? Yes. It's going to start with an initial speed, and when it reaches that max height, we know it comes to a stop. Like it has zero velocity. So we have kinetic energy on the initial. Now, uh, most of you might think that there is a force being applied because the person is actively throwing it. However, that throwing is before the object gets its speed. So while the person is doing work, that work is going straight into this kinetic energy that's resulting in this speed. Now, another way of thinking about this is that they don't tell us any information about work. There's no information about force, there's no information about the distance. So I'm going to say that there is no force applied. Yes, I know the person has to apply the force after he throws it, but the question is from the moment it leaves his hand to the moment it reaches the height. That's the scope of my question. I am ignoring everything that happens before and after that scope. So that's why I'm saying there is no force being applied in this range. No friction and no spring. So my equation is going to be Ke equals Pe. They don't tell me any of the energies. So instead, what I'm going to do is I'm going to replace Ke with 1 half mv squared and Pe with mgh. Plug my numbers in, solve for the height, and I get 20.4 meters. So easy peasy, lemon squeezy. All right, here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so going through this, there is no height change. It's a horizontal floor. Is there a speed change? Yes, it's coming to a stop, so it starts only with kinetic. Is there force being applied? No, not that we know of at least. Is there energy being lost? Yes, it clearly says it, so there's heat on the final, and there's no spring. So from here, we know that we have Ke equals Q. Once again, they don't tell us what the Ke is, so I'm going to plug in the equation 1 half mv squared for kinetic energy. There is no equation for Q, so it just stays where it is. Plus, we're actually looking for the energy loss, so we're going to leave it as Q. Again, we don't always plug in the equation for what we're doing. Plug the numbers in, solve for Q, and I get 600 joules. So that's how much energy is lost. We started with 600 joules of kinetic, we lost it all, therefore we lost 600 joules to heat. All right, here's the next set. Pause video, work stuff, and we'll go over in a second. So we have a person going down a zip line, landing some height. I'm not going to go through the 5 questions from here, but the main thing is that we start with potential from the height, we end with some speed because we're assuming that he starts at 0. That means I'm going to do mgh equals 1 half mv squared, plug the numbers in, and we get 37 meters per second. Now in part B, we're changing the mass. So everything about this beginning stays the same because the only thing that changed was the mass. So the substitution is going to go from 100 kilograms to 60. But it turns out we get the exact same speed. The reason being, if we look at this equation, we have a mass on both sides of the equation, which means I can drop it. Now, this is actually why doing the 5 questions is so important, because if you don't get into the habit of doing a potential equals kinetic, mgh equals 1 half mv squared, and instead try to calculate the potential and then see if you can substitute that into the kinetic energy equation as a second step, you'll find that there's going to be a lot of questions where the mass isn't given. So you might think, oh, I need mass to find the potential, but because it's going to be set equal to the kinetic energy, it just cancels out because mass actually doesn't matter in a case like this. And if we think about it, this makes sense because when we've dealt with free fall problems, having a ball up at an air and then dropping it to the ground, we've mentioned plenty of times that it didn't matter what the mass was. You drop a ball from a height of 1 meter and a bowling ball from a height of 1 meter, they hit the ground with the same speed. So this is the exact same problem. We start at some height, we go to the ground with some movement. The mass shouldn't matter, so it makes sense that they end up canceling out in the end. All right. Here's the next set. Pause the video, work itself. I'll go over in a second. All right. So here we have an 8 kilogram cart moving. Uh, the equation we're going to end up having is work equals ke plus ke. We start with work. It starts with an initial speed. It ends with an initial speed. Plugging the numbers in because again we don't have the kinetic energies by themselves, and we're looking for the work, so we're just going to leave work by itself. We plug the numbers in and we get 300 joules. Now, one thing that I want to bring up is if you noticed in the potential energy equation, the equation is mg delta h, which means that if we started at a height of 10 meters and we went down to, let's say, 7 meters, if we want to find the potential energy drop, we just put in that the change in height is 3. But we can't do that for the kinetic energies. We can't just do the change in speed being 5 because of the square on here. So we have to have an initial and a final speed put in. The next part, part B, we want to find the force. So we actually go back to our plug and chug. Work equals force times distance. Plug the numbers in, and we get that the force is 50 newtons. All right. Here's the next set. Pause the video, work yourself, and I'll go over in a second. All right. So when we do this, drop from the top, goes to kinetic, yada yada yada. Same old, MGH. Plug in the numbers in. We end up getting that the speed as it reaches that 30 meters is going to be 24.25 meters per second. Now, part B says that we find the speed to be 15 meters per second, and we want to know how much energy is lost. Now, this goes back to what I said before, that we can't just say, oh, the change in kinetic is, 1/2 mv squared, with v being the change in its speed. If you try to take the difference of these two numbers and plug it into the kinetic energy equation, you would get it wrong. What you'd want to do is restart the entire problem. So everything is about the same, except now we have some energy loss to heat. So what I'm going to do is I'm going to do this. PE equals KE final plus Q. So I'm going to use the same equation. This time I'm just taking what this is and plugging it straight into here. But this time the final velocity I'm going to say is 15 meters per second, and then I'm going to solve for Q. When I do that, I get that my energy loss is 3,267 joules. We just take the difference between how much kinetic energy we would have had if I did 1/2 mv squared with the original speed. I subtract the amount of kinetic energy I actually have with 15 meters per second, and I end up getting the amount of energy lost. All right, and that's all right. That being said, that's again going over all those questions. If you're still having some trouble, let me know. But again, it all boils down to using the 5 questions, being able to set up that equation. If you can do that, no conservation of energy question will ever be tough. Again, this is going to be the toughest part. Everything else is just going to be plug and chug. If you have any other questions, please let me know. Otherwise, I'll see you later. Good luck and have a great day.